Hey guys, so before we begin with the new chapter of normal distribution, let's have a quick recap of what we've studied up till now. So in the previous topics, we learned what a random variable is. We learned that a discrete random variable in particular is a random variable which comprises of discrete values such as 1, 2, 3, and so on. And the types of discrete random variables that we particularly studied was the geometric random variable and the binomial random variable. For the binomial distribution, we were looking at a number of successes, and they were all discrete values: 1 success, 2 success, 3 success, and so on. And for the geometric random variable, we were looking at the number of trials needed to reach a success. So we needed either 1 trial, 2 trials, 3 trials, and so on. These were all discrete values. And now, how do we define a continuous random variable? Well, a random variable that can take up any value or any continuous value is said to be a continuous random variable. For example, if you're looking at the weight of a person, the weight of a person can be 50.35, it can be 65.29. It is not particular to whole values, it can be any number on the number line. At the same time, if you're looking at the area of a particular property, or if you're looking at the height of a person, these are all continuous random variables because they can take up any value. And now, what is the relationship between a random variable and its probability distribution? Well, in the previous chapter, we learned that if we have a situation and it has characteristics which are of a discrete random variable, we can map that situation onto a discrete probability distribution. And the same goes for a continuous random variable. If we have a situation which has characteristics of a continuous random variable, we can map that situation onto a continuous probability distribution. And an example of a continuous probability distribution that we are doing, which we are going to do in this chapter, is the normal distribution. The normal distribution is a very important continuous probability distribution which will help us map real-time scenarios and calculate probabilities accordingly. So now let's learn more about the normal random distribution. The normal random variable is a continuous random variable. We already just learned this. And its probability distribution is called the normal distribution, which is also a continuous probability distribution. And now the question is, how do we compute probabilities of the normal random variable? Well, let me first show you the graph of a normal distribution. And now this is the graph of a normal distribution. It is a bell-shaped curve, as you can see, and it is symmetrical about the y-axis. Let's label the x-axis. The x-axis is for the normal random variable, which will be denoted as capital X. And for the y-axis, it is actually the probability density function PDF, which we have already learned what a PDF is in the first chapter. And now another thing to note is that this graph goes from minus infinity up to plus infinity. So it looks like this graph is touching the axis at 0. However, it is not. It is actually going all the way up to infinity and minus infinity from the left side. So basically, our domain of the normal distribution is minus infinity to plus infinity. And now, how do we calculate the probability of a normal random variable? Well, this graph is basically used because the area under the curve gives you the probability of the normal random variable. So for example, if you need to find the probability of a random variable from A to B, let's say you have a number A to B. And let's say A is somewhere over here and B is somewhere over here. How do we compute the probability from A to B? Well, we simply need to find the area under the curve, which is this part. So I'm just going to shade it over here so you guys can see. This is the area under the curve from A to B, and this portion will give you the probability from. And now, how does one find the area under a curve? Well, the standard rule is that we need to integrate the equation of the curve and we find the area under the curve. So what is the equation of our curve? The probability density function, as I said, has an equation. The probability density function's equation I will put right over here, which is basically f of x, and you can see how complicated this equation is. 1 upon sigma under root 2 pi e to the power minus half x minus mu upon sigma whole squared. This is the equation of our probability density function. This is the equation of this curve. Now, won't it be too complicated if we constantly have to integrate this equation, apply the limits? For example, in this case, if we apply the limits a to b and integrate this question, we will be getting a really complicated equation which will give us the probability. So what mathematicians have done to make this simpler is they have formed a table. They have formed a table which has probabilities. And all you need to do is figure out what these numbers are, or what the standard normal variables are, in order to find the corresponding probabilities. I'm sure you guys are a bit confused right now by the way I'm saying this, but I will be showing you this table in the next video so you guys have a better understanding of how to take out probabilities from that table rather than constantly integrating this equation. And now finally, let's talk about the characteristics of this curve. The characteristics of this curve. Let's just move everything a bit up. These are the characteristics of this curve. Number one, the curve is symmetrical. So as we can see, the curve is symmetrical about the y-axis. Secondly, the curve is centered at the mean. So basically, what I did not mention, which I will mention now, is that this center point over here, the center point of this curve is centered at the mean. This point is actually mean, which is mu, denoted as mu, and it is centered at the mean with its peak at the mean. Also, you can see that this curve has no skewness. This is also a concept that we studied in the first chapter, that there is no skewness. So curve is not positively skewed or negatively skewed. There is no skewness, and when there is no skewness of a particular curve, the mean, median, and mode are all equal. Therefore, this mean over here is equivalent to the median, which is equivalent to the mode. And lastly, the total area under the curve. This total area from minus infinity to infinity. If we integrate this equation, or if we find the probability from infinity to minus infinity, you will find out that the total probability is equivalent to 1. And so these are the properties of a normal distribution. And so now in the next video, we'll be learning how to compute probabilities, how to solve questions where we can simply, rather than integrating the probability density function, we can simply look at the standard normal distribution table to compute probabilities.